Hello, my name is Eric Normand, and these are my thoughts on functional programming. I wanted to talk about a functional programming pattern, a coding pattern that comes up pretty often in functional programming, and I think it's something that's really cool, and it needs a name. It doesn't have a name. So I need to come up with something. But let me describe the pattern. Maybe you can help me. So let's say we need to do some calculation, some operation on a value. And we're looking at this value and this calculation we're supposed to do, and it just seems really tedious to do. But if we take this value, which has a certain type, and we take that value and we transform it into a new type. Sometimes with that new type, the operation is so easy, right? So you do the operation on the new type, and I'm going to call it a new space. You're like lifting it up into a different space that has maybe a richer format, a richer amount of information, right? It's a different space where the operation is much easier to do. You do the operation, and then you lower it back down. Let me give an example. So if you had to add, you had some text, okay, and the text has lines in it, has new lines in it. So it's a string. And I ask you, can you add a semicolon to the end of every line? Well, that can get kind of hairy. I mean, sure, you can do a little bit of magic with regexes or something, but you can't do it. I could make it just a little bit more complicated, like add a semicolon if it has an even number of characters in the line, and a period if it has an odd number, unless the first letter is a T, the first letter of the line is a T, then put a hyphen, right? And so I can just make it like weirdly complicated, right? And so you're working on this string. What do? This problem becomes really hard. Like, you got all these lines in this string, and where do you put the hyphens? How do you count between new line characters and stuff like that? It's just the wrong structure to be working on this kind of problem. So what you do is you lift it up. You take this string and you say, this is the wrong type for solving this problem. I'm going to turn it into a list of strings where each string is a line. So I'm going to split on new lines. And when you split on new lines, now you've got this new type. You're in a new space. It's actually a richer space in the context of your problem. And it actually becomes an easy problem to solve. Right? You count up the number of letters or characters in the line, and you do the right thing. And then, once you've modified each of the lines, you just join them together with new lines. So that's your lowering, turning it back into a string. Now, this is a very common pattern in functional programming. You're taking a thing where it's hard to solve this problem for whatever reason, like it's actually just complicated, or there's a lot of corner cases in that data type. You lift it up to a new space, do your thing, and then you lower it back down. You have your answer. Another example that I really like to give, because it shows something interesting about math. So if you had to calculate the average of some numbers, we all know the formula. You add up all the numbers and then you divide by the count of the numbers. But then what happens if the count is 0? So if you have an empty list of numbers, you have this corner case of 0, and it crashes your whole program if you try to do it. So you have to check, is it 0? But then what do you even return? Because you can't, you can't return 0 because that's not true. The average wasn't 0. You don't even have an average. It's impossible to calculate. It's undefined. So you have this corner case of 0. So what do? Well, what I like to do is to lift up the numbers into a higher space, a more interesting space. And I say each of those numbers is actually an average. It's an average with count 1, right? And an average is a ratio, which means it's got a numerator and a denominator. And so I store those two things. I store a tuple of a numerator and a denominator. And so I take each number and I just pair it with 1. So now I've got these things that I can call, each of them is an average. Now notice, if I have a pair of numbers like this, I'm never going to have a 0 with any of these numbers. So I never have this corner case. I can always, not with these, if I lift them, right? I can always lower them back by dividing. Just divide the two numbers. So that's my lowering operation. And if it's got too much wind over here. Okay, so then I have also a representation for this 0 case, right? I can say there's no mathematical problem with representing the tuple 0, 0. It doesn't hurt anything. They're both the additive identity, and that's what I want. Because you add up the top things and you add up a bunch of normally 1s for the denominator. But I can put in a 0 and it won't change anything. So I've got this new type, which is a richer space, where I can add up these averages by adding the numerator and the denominators, and then later I can divide them if I want. So I've removed that corner case, but I've also gotten all these great algebraic properties from it. Because now that I'm just adding, I'm in a space where I'm only adding, I'm never dividing. And addition is commutative and associative, right? So now I'm operating in this really rich space. Because they're associative, I can group them however I want. I can send them off to different people to work on, to different computers, distributed. They can work on them independently, grouped however I want. I can just take the list and chop it up like this, chop, 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 send off the different pieces to be averaged, to be added together. They send me back the answer. I add those all together, and I've got an average of all of them. And then the problem is lowering, because now we have we can't really lower our 0, 0 case. We might have that at the end, like we might have had an empty list, but we can save that for later because we actually have a marker. We have a value that represents that case where we didn't have any numbers. So we've actually gained something, but we do have to remember that we have that kind of sentinel value that, like, do not lower this one, right? But we can, we're not representing the lack of average with a 0 or something like that, like we were trying to before. Okay, so we've gained something, And it's a cool pattern. You see the same thing. We're lifting it up to a richer space, doing an operation, and lowering it back down. I don't know what this pattern should be called. Lift and lower? I don't know. Yeah, anyway, I think that this is a pattern we need a name for. It's something that we do a lot, and I want to talk one last thing about how we how can we, what do we need to do this pattern? Well, obviously we need to identify the richer space somehow, right? But we also need this property, this inverse, we need the lift and lower, which are inverse property or inverse operations of each other. So that is not always possible. Oh, here's another example. I was trying to think of some good examples that are in a different domain. Parsing and unparsing. Similar to the text one we had before, but let's say you have some JSON. You can parse it into your language, operate on it, pull stuff out of the hash maps and, take stuff out of the arrays, count stuff up, and then change it, and then you can lower it back down into a string. And now you can store it somewhere on a disk, or you can send it over the wire. That's where it was before. It's a string, you parsed it, so you've lifted it up to this richer representation. You do your thing, and then you unparse it, you serialize it back down to JSON, and you're good, right? We do this all the time. We just often don't think of it as this pattern, this lift and lower pattern. Okay, so we need that lift and lower, and they need to be inverses of each other. This is a strict requirement of this pattern. And then identifying that richer space is not always easy. Like with the averages, I couldn't do that when I was a beginner programmer. That was not the way I was thinking. But I do have to say, if you start looking for these patterns, if you start looking for this richer space, just ask yourself the question. You're looking at a problem and you're like, oh, it's kind of hard. Well, in what data type, in what structure would this problem be easy? Right? Would it be easy if I already had the thing split up on lines? I think so. Right? Because that much more closely resembles the problem that you're dealing with. It models the structure of the problem. So, keep that in your mind. That question, just have it all the time. When you're having trouble, just think, is there a representation where this is easier? Where this is trivial, even? Is there a representation where this is a trivial problem? And can I make this representation turn into the representation I have, can I make it turn into the representation I want? And can I go the opposite direction? Because you have to be able to go the opposite. If it's lossy, you can't do this pattern. If you can't generate the lower. So what would be lossy? Well, I could do something like, if I just needed to, well, I could have if I needed to know the length of the lines, I could do some function that counted characters between new lines and gave me a list of the counts of the lines, the lengths of the lines. But I've lost all the characters, right? I only have numbers of counts of lines. So although it might be easy to know which line to add a semicolon to because of the counts, I can't go back. I've thrown away information. What you're looking for is a thing that has more information. Store more information. So I see this often in Clojure where people get a loop. They get a loop going, and they're like, but how do I keep track of this thing and this other thing? Because they're used to having mutable variables that they just modify throughout the loop. And I'm like, well, just bundle it all together. Just put it in there. Put it in the value. Right? Keep it all together. And that's the thing that's going through the loop each time. And what you notice is, this is one of John Hughes's principles. John Hughes, one of the creators of Haskell, also the creator of QuickCheck, the original Haskell QuickCheck and the Erlang QuickCheck. John Hughes, like one of the great living functional programmers in the world, and at least on the academic side. He talks about using whole values. And he speaks about it a little bit mysteriously, like, what do you mean by whole values? But this is what he means. He means instead of having 4 mutable variables that you're modifying, and this iteration through the loop, we're going to change this one, and then we're going to look at this one, and then that changes that one, and you're doing all this manipulation, you get the answer. I'm not going to be like snobby about it. You get the answer. But when you're moving into functional programming, you start to look at, well, why don't I keep all of these together in a single value? And then have operations which modify them in well-defined ways. Hopefully they have some kinds of interesting algebraic properties, so I'm not stuck in an iterative loop. If they have commutative, or if they're commutative or associative, I can do interesting stuff distributed. I can do a divide and conquer kind of algorithm. Much more interesting, much more distributable, much more parallelizable. So that's what you're looking for, these whole values. And so often what you're doing is you're taking a value and your lifting operation, your lift, so there's 2, there's the lift and the lower. So the lift operation is just adding in extra information that will be useful when you're solving the problem in your algorithm. And then you solve the problem, and then the lower is throwing away that extra information. That's very often what it's going to look like. All right. This has been a lot of fun talking about this lift and lower pattern. Might be what it winds up being called. And I think this one might actually go in my book. I think this is a cool one. Very, very awesome pattern. Whenever I find it, I'm like, yes, this is cool. Because, it chains so well. You know what I mean? It threads really well. You say, here, this is the value I have. Lift it up. Do the operation, do the calculation, then lower it down, right? It just chains right through. Awesome. See y'all later. Bye.